Polynomial identities. This is a really important unit. It's not hard, but for some of these identities, it does take some practices. Let's take a quick look over this. To begin with, difference of squares is really important. Some of the more advanced students basically, for them this becomes second nature. But if you find yourself not as fluent in identifying difference of squares, make sure you do enough practices. This will really help you along the way. Square of a sum. That's really, there's no magic to it other than distribution. If you do a plus b square, a plus b times a plus b, that's how you get it, right? Difference of cubes and sum of cubes. We're going to cover more about that. These have something to do with binomial theorem, which we'll cover at the end of this unit. Regardless what it is, you should be very fluent in identifying how these identities are related to each other. And so, for example, if I give you something that looks a plus b times a minus b, you should be able to recognize it right away and rewrite it into a squared minus b squared. So here's an example. How can we prove the sum of cubes identity? I'm going to leave this to you. There's no magic to it. You take the right-hand side right here and right here, right? And start to distribute them one by one. And then distribute the b. And simplify it, you will get to a cubed plus b cubed. I do want to ask you, what is the trick to remember this? How can you remember this? And can you prove it? This one, it's hard to prove with geometry. But what other ways that can help you to remember this identity? Okay, if you have questions, bring it back to class. We'll answer it there. This one is a binomial, so the entire sum is being raised to the second power. So what we're thinking of using is this one. A squared plus 2ab plus b squared. In this case, your a is your 2x squared and your b is your y cubed. So if you go by that, you should have 4x raised to the fourth power plus 4 2ab x squared y cubed plus y raised to the sixth power. If you want to write it out more formally, that's our conclusion right there. Okay? Difference of squares, right? A squared minus b squared equals a plus b times a minus b. And especially for those students who are not as fluent in this yet, I highly encourage you to write the equation, the identities like I did up on top. This will really help you. And now from this you can tell a equals 3m squared, b equals 5n cubed. And then you just simply plug it in. So this becomes 3m squared plus 5n cubed times 3m squared minus 5n cubed. That's your final solution. Sometimes these have different degrees here. If they have the same degrees, sometimes you can factor them out even more after this step. Just watch out for additional factoring by using the identities. We're going to begin to study binomial theorem. You cannot study binomial theorem without understanding Pascal's triangle. So here is a question that leads to that. How is x plus y raised to the n obtained from x plus y raised to the n minus 1? So in other words, how do we get let's say x plus y raised to the fifth power from x plus y raised to the fourth power. So obviously it's just you multiply one more thing. But what kind of relationship do they have? So let's watch this video.
How is x plus y to the power of n obtained from x plus y to the power of n minus 1? Look at an example. Part A. What are x plus y cubed and x plus y to the power of 4? X plus y cubed is x plus y times x plus y squared. Squaring x plus y gives x squared plus 2xy plus y squared. To multiply x plus y by the quadratic, you need to multiply each term of the quadratic by x plus y. First, multiply x squared by x and then by y. Then do the same for 2xy and y squared. Combine like terms to find the simplified polynomial. This simplified polynomial is x plus y cubed. To find x plus y to the power of 4, multiply x plus y by each term of the cubic expression. Then combine like terms to find the new simplified polynomial. This simplified polynomial is x plus y to the power of 4. When the calculations are simplified, you can start to see a pattern. The coefficients of x plus y to the power of n are produced by adding the coefficients of x plus y to the power of n minus 1. This produces an array called Pascal's Triangle. Pascal's Triangle is a triangular pattern of numbers. In this pattern, each number is the sum of the two numbers diagonally above it. For example, this 6 is the sum of the two 3's diagonally above it. If there is not a second number diagonally above in the triangle, think of the missing number as 0. So this 1 is the sum of the 1 and a hidden 0.
So here's the Pascal's Triangle. I have a project for you guys which is really fun. I will forward it to you. Here is a summary of binomial theorem. It looks confusing, but don't be confused by it. There is a pattern to it, which is when you talk about a plus b raised to the nth power, you first notice that the coefficients right here are the numbers in row n of Pascal triangle. So if you're cubing a plus b, you use the third row. If you're raising it to the 15th power or 1,000th power, you go to the 15th and 1,000th row, right? Obviously, for simple calculations, we're not going to do that high of a power, but that's how you handle the coefficients. And then for the degrees of a, it's going to go from the highest to the lowest descending order. Then for b, so it goes from n all the way to 0. A raised to the 0 is just 1. For b, it's the opposite. It's from 0, go all the way up to n. So what looks confusing is actually making a lot more sense. Okay, I also gave you an image of Pascal triangle. Read through it. It's like I said, it's one of the most fun and interesting discoveries in math. Use the binomial theorem to expand the expression. So in this case, it specifically says that we have to use the binomial theorem. Then you know that Pascal's triangle comes into play. So let's see. Binomial theorem, I have, so the first term, I have x. The second term, so I'm going to call it a. The second term, notice that I have -3. Be careful with that, okay? So with this kind of binomial expansion, what I do is once I identify which is the first term, which is the second term, I know the first term starts with the highest degree. right? And then the second term starts with the lowest degree, and then it builds up. Did I get everything? 1, 2, and then one more. From 0 to the given power. That's my setup there for the two terms. I still have to worry about my coefficients, and this is where I need to graph a Pascal triangle in here. So this would be 2. Make sure they're all lined up. Notice that how I made sure that 1 plus 1 gives me 2, and now 2 plus 1 would give me 3, and over here it gives me 3, and then it's 1 on the side, right? And then that's 4, 6, 4, and it's 1 on the side. If I want to go down more, that's 10. This is 10. This is 5. There's 1 there. This is 5. And there's 1 on the side. Since I'm looking the power of the fourth power, I'm looking at the fourth row, not including the top one. So 1, 2, 3, 4. This is the row that I need. I literally take the numbers there, I plug in to each one of them, and then here's a 1. That's it. It looks really messy, so I have to simplify it. So if I simplify this one, it would be x raised to the 4th. This would be negative 12x cubed. This is 954x squared, and that's 12, that's a 27. That would be 108 negative x plus 81. That's my final answer. Okay, to recap, I used binomial theorem to go take the first term from the highest degree to the lowest. Then I take the second term from the lowest to the highest. And then I worry about the coefficients with the Pascal triangle. If you feel more comfortable to address the figure out the coefficients first, that's totally fine too. One common mistake is here. As the power for the first variable going in descending order and the second one going in the ascending order, it's easy to get confused. My quick check is that when I add the two of them together, it has to be the same. It's always 4 in this example, right? 3 plus 1, 2 plus 2, it's always the power of 4. I also make sure that I double check with each individual term, literally going from descending or ascending order. All right? Here's a really challenging question. How can you use a polynomial identity to generate Pythagorean triples? Remember, a Pythagorean triple is just any set of 3 positive integers that satisfies a squared plus b squared plus equals c. So here I gave you a right triangle, and the two legs are a and b respectively, and the hypotenuse is c, and we know that a squared plus b squared equals c, right? So some Pythagorean triples are well known, like 3, 4, 5. So 3 squared plus 4 squared equals 5 squared. And there is a polynomial identity that's generalized that you can use to generate an infinite number of Pythagorean triples. See if you can derive that yourself. And if not, we will talk about it in class. As a recap, these are the 4 identities that you're expected to be very fluent with. And there's also the binomial expansion, which is based on the Pascal triangles. Okay? And don't forget to finish the project, and I look forward to getting your finished products. It's really a lot of fun. Finally, for those who are always hungry, because especially the teenage boys, and I've got 2 of you in my house, it would be nice if you do something like this for your parents one day. Enjoy it.
Yo, this is how you make shrimp fried rice. Ooh. So you're gonna need your rice, onion, carrot, eggs, shrimp. Basically, it's 1-to-1 ratio with 1 rice and 1 of everything here. We're gonna start with a splash of oil, eggs, another one. Scramble that joint up. Put your egg to the side. A little bit more oil, half a tablespoon of garlic, about 3 tablespoons of scallion. Woo! That's what we call pagitum right here. 150 grains of shrimp. Once the shrimp is cooked about 80%, throw in your onion, 50 grains of carrot, season it with salt, pepper. Yo, anything is good with salt and pepper, but this is my secret. Butter. Throw in your bowl of rice, a tablespoon of soy sauce on your rice, half a tablespoon of sesame oil. Now break that joint up, baby. Put your eggs back right in. Woo.
So have fun with it, all right?